I think we should. We have got, and people would keep joining, hopefully.
Yes. Yeah, we can start, I believe, Dr. Khalid, because some people have some other commitments after that. So
exactly.
Yeah.
So good morning, everyone. Thank you so much for joining us for today's session. We have our guest speaker, Dr. Amin Amiri, and I would not take so long for the introduction. He is a research fellow at our department at Lakehead University, and he has got tons of experience in academia and research. So welcome, Dr. Delouei. Hopefully I pronounce your name correctly. And all the best for your presentation. So we would go for the presentation in the first 40 to 45 minutes. And then at the end, we would have the questions and answer session from the audience. So thank you so much for joining, and it's over to you now.
Thank you, Dr. Khalid, for inviting me to
I
this
think you can, sorry, you can share the screen now.
Yeah, I want to share my screen now. Okay, is it okay?
Yes.
That's good, yes.
Yeah. Hello, everyone. My name is Amin Amiri, and I hold a PhD in mechanical engineering. Currently, I am a research associate at Department of Mechanical Engineering at Lakehead University. My seminar is about hybrid approaches for moving boundaries. I will introduce immersive boundary lattice Boltzmann method and also lattice spring model to simulate the fluid structure interaction. The contents of my presentation include an introduction to the fluid structure interaction, and after that, I will have an introduction to thermal lattice Boltzmann methods that followed by immersive boundary lattice Boltzmann method. In the next section, I will introduce lattice spring IB-LBM model for simulating flexible boundaries. And at the end, I will discuss our progress on this hybrid method. As an introduction, I want to speak about the fluid structure interaction problem, FSI. We can say that FSI problem deals with the interaction of the structure with their internal and surrounding fluid flow. As you can see in this figure, that there is a lot of flexible filaments in interaction with surrounding fluid flow. But you should consider that this interaction is a function of several parameters, like the form of the structure. It can be in fixed or in moving situation, and also it can be solid or flexible. On the other hand, the fluid flow can be in Newtonian or non-Newtonian form, and all these parameters will affect the interaction between the solids and the surrounding fluids. In our research, we suggest a hybrid method that can address all of these parameters, including solid, flexible, fixed, or moving structure, and also the non-Newtonian behavior in fluid flow. For solving the problems of the problem include the fluid structure interactions, there is two main categories. One of them is body conformal mesh methods, and another one is fixed mesh methods. In the first category, we have a flow solver to find the behavior of the fluids And if we have a moving mesh, moving boundaries, you should have a mesh movement according to the movement of the particles. And for each time step, you should have a remeshing. This figure illustrates this situation. As you can see, we have three particles in a fluid domain, and you should you should have a complicated unstructured mesh to match with your boundaries. And the other problem is that when you have a movement, I mean, in the next time step, you should have a remeshing to capture the new position of the particles, and it's really time consuming, and it is computationally expensive. But in the second approach, we used fixed mesh methods to solve this problem. Again, in this method, we have we have a fixed Eulerian domain that is related to the fluid flow. And on the other hand, we have some Lagrangian nodes, as you can see in this schematic, that shows the immersed boundary. These two nodes or mesh grades are completely separated to each other, and we have a free movement of Lagrangian nodes between the Eulerian nodes. But the problem is that the connection between the Eulerian and Lagrangian nodes, for this reason, we will use the different interface scheme that I will discuss them in detail in the next slides. But as you can see here, there is no need to have a remeshing for each time step, and also the frame of the domain is in Cartesian form, which will reduce the computational cost of the problem and simulation. One of the well-known methods for free meshing approach is immersed boundary methods. The term of immersed boundary was first introduced by Peskin for cardiac flow. I think that he introduced this method in 1972 as a part of his PhD thesis. And until now, there is a lot of development to his method, and now we have a more advanced IB-LBM algorithm based on the initial methods that introduced by Peskin. In this slide, I want to have a comparison between immersed boundary method and the common body conformal grade methods. As you can see here, and we discussed, the IBM have a Cartesian frame that enable us to have a parallel programming, and also to match with other Cartesian frame like Lattice Boltzmann method or finite difference methods. On the other hand, there is no need for remeshing, so we have low numerical cost, and it's suitable for moving objects. On the other hand, there are some disadvantages for the immersed boundary methods. The main problem is with the boundary conditions. Applying boundary conditions on the immersed boundary methods are depend on to the interface schemes that can reduce the accuracy of the method, and you should be cautioned about this problem. One of the methods that works very good with immersed boundary methods is Lattice Boltzmann methods. There are several reasons that we choose Lattice Boltzmann method to solve the fluid domain of our solution. One of them is Cartesian grade that simplify the complex boundary conditions of the problem. Also, Lattice-Boltzmann method is based on the momentum exchange that enable us to calculate the force on IBM easily. Another one is mesoscopic nature of the LBM of the Lattice-Boltzmann method that help us for simulating flexible boundaries in IBM. Also, there is another options like stability in multi-phase flow and parallelism ability that help us for simulating larger scale problems and also increase the applicability of the hybrid methods. These advantages between LBM and IBM encourage us to combine this method as a new hybrid method of immersive boundary lattice Boltzmann methods. I can say that our initial research on this subject returned to 2014 when we have paper in Physical Review journal with a cooperation of Professor Sushi, who has affiliation in Rome and also in Cambridge University. And he has a very famous book on, a well-known book on Lattice-Boltzmann method. At that time, I think it was a leading research, and we get and it helped us to recognize as a leading research group on this method. In brief, if I want to say the application of the FSI problems or lattice or immersive boundary Lattice-Boltzmann method, I should say that it can be applied for bioparticulate flow, or we can use it for modeling the flights and other aquatic movement. In chemical engineering, you can use it for simulating the separation of solids and fluid phases. And also in heat transfer, you can model direct contact exchanger by using of this method. Another one is the natural non-Newtonian flows, like the flows of the lavas. And in our research, we cover some of this application that I will present them to you in the end of this presentation. To introduce Lattice-Boltzmann method, we first should speak about the macroscopic, and we can compare the macroscopic and microscopic scale. In this figure, you can see the common and typical fluid dynamic problem scales. And as you can see, for the smallest scale, we have the micro scale. The micro scale is in dimension of a molecule, and we can say it's about a nanometer. And the governing equation for this scale is Newtonian. And numerical method that used for simulating this kind of the problems are molecular dynamics. On the other hand, we have a macro scale that is more than a micrometer, and the physics of the problem is continuous, and the governing equations are Navier-Stokes equations. There are a lot of CFD tools that can help us to simulate problems in this scale. But there is another scale between the micro and macro scales named mesoscale, that is between the nano and micrometer. And the governing equation in this scale is Boltzmann equations. Our desired method, I mean Lattice-Boltzmann method, is in this fall in this scale, and it has some advantage of both micro and macro scale. For example, we have not too much computational cost like the micro scale, but on the other hand, we can capture some physical phenomena related to the micro scale by using the Lattice-Boltzmann method. So nowadays, a lot of the researchers are interested in this method. And in this method, instead of working with a single molecule, we work with a bunch of them, with a group of them, and we define a distribution function that is a density of molecules with a certain velocity and location at a specific time. By using this distribution function, you can define the local properties of a thermo-fluid problems. I don't want to speak more detail about this distribution function, but you should know that in Lattice-Boltzmann method, we don't work with the Lattice-Boltzmann formulation. We work with a discretized form of it in a certain direction, as you can see in the right-hand side figure. And we show the probability distribution function in a certain direction to find different properties of the fluids. Also, I should mention that in discretizing of Lattice-Boltzmann equation, the researchers consider two different steps. One of them is collision and another one is streaming. And by combining these two a stage or a step, you will find the Lattice-Boltzmann techniques algorithm. And after finding the distribution function, you can find the macroscopic properties based on the probability distribution. But the problem that are interested in our simulation was the forcing in Lattice-Boltzmann equations. For combining the Lattice-Boltzmann method with immersed boundary, you should have a forcing term in your Lattice-Boltzmann equations. There is two ways generally to apply a forcing body in a Lattice-Boltzmann equation. One of them is lumped forcing and another one is a split forcing. In lump forcing, the body force is applied in a single time step, but in a split forcing, we have two body forces that applied in the first and second half of the time step. The second one is more accurate and we have a more smooth forcing process in this form. And also it can recover the Navier-Stokes equations with a second order accuracy. The next step in our hybrid method is to combining the immersed boundary and Lattice-Boltzmann method. For immersed boundary method, as I told you, we have two different nodes, Eulerian and Lagrangian nodes, and they are independent to each other. And you should use interface scheme, as you can see in this figure, to have information exchange between Eulerian and Lagrangian nodes. The accuracy of the IBM are depend on to this interface scheme. Again, in general, there is two different interface scheme, especially in immersed boundary Lattice-Boltzmann method. One of them is diffuse and another one is the sharp interface. And the diffuse one can subdivide it to explicit and implicit. For diffuse direct forcing IB-LBM, as you can see here, we have two forcing steps. One of them is between the streaming and collision step, and another one as a second forcing is occurred after the collision step. In the first forcing, there is an information exchange between Eulerian and Lagrangian nodes. As you can see here, at the first step, we should update the velocity of the Lagrangian nodes based on the velocity of the Eulerian nodes nearby to each Lagrangian nodes. And after that, we can use these forces and compare it with desired forces that come from the Newton equation of motions for Lagrangian nodes, and find a desirable velocity that can distribute again to the Eulerian nodes. You know, this process helps us to identify the effect of the immersed boundary onto the Eulerian or fluid domain. We can repeat this algorithm several times to give more exact solution for force and also updated velocity. In this form, we will have an implicit algorithm. Also, we can repeat this procedure for finding the desired thermal or temperature distribution on moving boundaries too. So we applied the direct forcing for both fluid flow and heat transfer in a moving boundary as an extension of our work respect to the prior workings. As I told you, interface scheme has a very important role in IBM. There is, for example, for diffuse interface scheme, based on the number of the points that incorporate in our simulations, we may have 2-point, 3-point, 4-point, or 4-point cosine interface schemes. And you can see the values of distribution function that are used for different interface schemes in this figure. When I encounter with this problem, I make a question from myself, and the question was, does increasing computational point improve the accuracy of the simulation or not? Based on these questions, we start research on the effect of this interface scheme on the accuracy of the solution. And it was our first paper on 2015 that I will discuss about that. After that, I introduced the sharp direct forcing IB-LBM too. As a second approach for interface scheme, we can speak about the sharp algorithm. Again, in sharp algorithm, we have a first forcing and second forcing for a split forcing algorithm. And it happens between a streaming step and collision step, and also after the collision step. In the sharp interface, we have some interpolation to find the desired velocity or exact velocity on Lagrangian and Eulerian nodes. Here, we have no interface scheme, but finding these distances are not so easy. And I think that the implementation of the sharp schemes are more complicated in comparison with the diffuse one. But to ensure about the right interface scheme, we start with a benchmark of the fluid flow and also heat transfer over a stationary cylinder. We find different hydrothermal parameters of this problem, these benchmark problems. We found that for this benchmark solution, by considering drag coefficient and Nusselt number change with the time, and also with the power law index that I will introduce in next slides, we found that the 4-point diffuse interface scheme has the best results for our solution. indeed, the sharp interface scheme has the less computational cost for that. But I encounter with some stability problem when I use the sharp methods for moving boundaries. Also, I found that the increase of the neighboring Lorentz nodes are not helpful to increase the accuracy of the work, both for hydrodynamic and heat transfer over a cylinder. Um, As another benchmark that he used for testing the hybrid methods and also other methods that he used for moving boundaries, free fall of a particle in a Newtonian flow was considered. We also test our method with this benchmark problem. As you can see here, we test the longitudinal position and velocity of falling particle in Newtonian fluid. And as you can see here, our methods can capture the phenomena related to this problem in a good agreement. Only we have some problem on the bottom of the container, and I can say that these differences are related to the collision methods that we used in different methods. I will discuss this issue in the future section 2. As another benchmark, we have cooling of falling particle again in a container and in Newtonian flow. As you can see here, for this benchmark, the researcher used sedimentation of isothermal hot particle and cold particle inside the container, and after that they calculate the drag forces as a function of the terminal Reynolds number. Again, as you can see here, or new or suggested hybrid methods can capture the results or have a good agreement with the results of the others. One of the issues related to the immersive boundary methods are the particle-particle or particle-wall collision models that the different researchers used in their studies. Most of these studies are done on circular particles, and for finding the forces between in collision process, they use the particle center and the distance between this particle center to find these forces. You know, this formulation works very good for circular particles, but we found that in non-circular situation we have some difficulty. But for circular one, again, we validate a benchmark that is related to the falling of two particles located in the top of a container, and we can capture a phenomena here that's known as a drafting, kissing, and tumbling, or DKT. DKT is related to the to three different stages. In the first stage, two particles followed each other and they close to each other. This state is drafting, and after that they touch each other. That is related to kissing, and after that we have unstable situation that are named tumbling. Most of the methods have the same trend and the same values for the first two stages, but we have different results after the kissing, because tumbling is an unstable situation. And here again, as you can see in these figures, can capture the first two stage, and again our results has some differences with other methods, but it's in acceptable range. And also in the next step, we used lattice spring model to enable our code or hybrid method to dealing with flexible boundaries, as you can see here. In this approach, we used some network of the Hookean spring to model the elastic solid and to capture the flexibility of the immersed boundary. Again, we used a benchmark problem that is related to the fluid flow over a cylinder mounted to a flexible filament to validate our hybrid method. As you can see here again, our hybrid method can show the changes related to the flexible boundaries, and it has a good agreement with the work of the others, I mean Tian et al. After validating of and also verification of our models, I want to explain the progress of our research related to these hybrid methods. At the first step, we decided to capture the non-Newtonian behavior of the fluid flow in the presence of the moving boundaries. But as a benchmark, again, we consider fluid flow with different non-Newtonian behavior, I mean shear thinning, Newtonian and shear thickening fluid over a cylinder, not isothermal cylinder, and we capture the phenomenon in different fluid flow regimes like creeping flow, STD flow, and also unsteady flow. And as you can see here, we can see the symmetric and also the von Neumann shedding in all the situation, and also we can see the differences between the shear thinning and shear thickening fluids. After that, in a research done in 2016, we focused on different shape of the particle, of the falling particle. And you can see an example here. For example, we can capture the movement of a square and also a triangle in a fluid flow. And again, we do it for different non-Newtonian fluid flows. Also, you can see the angular velocity as a function of the time for different particle shapes. After that, our research team works more about incorporating thermal properties in our hybrid methods. For this one, we decided to capture transient particle temperature in our method. For this purpose, we developed our method for capturing varying temperature in moving boundaries. We used some equation related to the energy balance and find some methods or developed some methods to capture the temperature change or lump temperature change in the free falling of circular particle. You know, this simulation are so important for modeling of direct heat exchangers. In the next step, we decided to modeling the Ducati phenomena in non-Newtonian fluids. We do it for the first time, And we have no literature before that about this phenomena in non-Newtonian fluids. We can capture the starting time of the drafting and kissing steps as a function of the Power law index related to the non-Newtonian behavior. We did it for the first time, and I think that it can be considered as a benchmark problem for investigating the collision process in non-Newtonian fluids. And we get several citations for that, I think more than 70 until now. That shows that it has this potential to be a benchmark for this problem. At the next step, in one of our recent research, we work on pulsating boundary conditions. We use this simulation to investigate to investigate that how we can control the collision between the particles, but by using a pulsating boundary condition in our applications. And as you can see here, we can capture the differences between the collisions steps in the presence of the pulsating boundary conditions. For example, you can see the longitudinal coordinate of particle and also transverse coordinates of particle under pulsating conditions. As I told you, one of the issues with the previous works on collision or particulate flows was the method that they simulate the collision. They use the center of the circular particles to find the forces between the particles and also particle and walls. But there is some problem for the particles that are not in circular form. I mean for non-circular particles, especially those one has sharp edge. For example, for triangles. In our hybrid methods, we developed a new collision approach based on the nearest boundary distance. I can say in brief form that we did not use the distance between the center of the particles to find the forces between them. We use the distance, the nearest distance between the Lagrangian nodes to find the appropriate fluid flow, the collision force, and we tune it based on the benchmark problems. We used this new approach and simulate different problems like these ones. As you can see here, we model the free falling of several particles with different shapes and size at various time stage. You can see that this new collision methods can capture this sedimentation in a very good manner. Also, we decided to use our hybrid method for different practical applications. For example, infiltration of the particulate flows by using a porous media. We use this hybrid method to design optimal porous media to have best efficiency for our filtration process. For example, in this figure, you can observe the effect of different arrangement of the porous media on the efficiency of the filtration of particulate flows. For example, we found that if we consider big obstacle in the first step, then we will have a better results. Or also we used also we studied the effect of the particle shapes of the porous media on the again on the performance of our filtration, and we found that in the mixed situation, when we have both circle and square shapes, we have a better performance. You can consider it as one of the application of this hybrid method. And at the end, I want to present to you our recent works on flexible filaments. Again, we developed our codes for capturing the flexible structures in both Newtonian and non-Newtonian fluid flow. And we can capture a lot of well-known phenomenon that are related to this kind of the problems. For example, there is a configurations that named orbit 8 configurations that can capture in the vibration of flexible filaments. And as you can see, our hybrid methods can capture these configurations in different fluid flow. I mean, in shear thickening Newtonian and shear thickening ones. And I should mention that we validated or result for Newtonian ones. This feature can help us for simulating the bio movement, especially in different non-Newtonian fluid flows like the blood flows. As a summary of my presentation, I should say that hybrid IB-LBM can effectively simulate fluid structure interaction, and it has higher speed in comparison to the body conformal mesh methods. But about the accuracy, you should be aware about the interface schemes that you used for different fluid flow regimes. It can capture non-Newtonian behavior by the help of the local properties of the Lattice-Boltzmann equation. Also, our new collision model help us to support various collision algorithm even for non-circular shapes. These methods are effective for complex flows like pulsating flows or in filtration applications, for example. And also the lattice spring model that added to our hybrid method help us to simulate flexible boundaries in an effective form. At the end, I want to thanks Dr. Khaled and also Dr. Tarok and Mechanical Engineering Department of Lakehead University that give me this opportunity to have this presentation. Thank you for your attention.
Thank you so much. Thank you so much, Amin, for this wonderful presentation. And we definitely are pleased to know more about your research. It is very exciting. And now we open the floor for questions from audience. So I would really encourage everyone to ask questions and to make it like a more engaging seminar. So I would read the questions in the chat box as well if someone wants to write it over there, but definitely you can raise hand and go ahead with your question. Okay, so by the time I think some people think about their questions or they think about framing their question, I mean, I have a couple of questions. What do you suggest about the suitability of this diffuse interface IBM for high-speed flows. Yes, we have seen a lot of application in literature for low-speed flows, but what is your comment on that?
Yeah. Thanks for your questions. I know that I'm familiar with your excellent work. I know that you use the sharp interface for simulating your FSI problems. You know, it was my experience. I do my simulation in different Reynolds number, especially for Reynolds number of 100. I have some problems with the stability of the sharp methods, and I forced to use the 4-point diffuse methods to simulate my problems. Another reasons that I choose the diffuse interface was the easygoing algorithm of that. You know, most of my students and also myself has a lot of problem with finding the differences, the distances in sharp methods. You know, finding delta in sharp methods are not so easy, especially for more complicated boundary conditions. And I should mention that for my cases, for the cases that I work on it, I compare my results with the results of the others and also with some analytical results. And I found that the diffuse interface is more suitable for my simulations. But I should mention that for different application, the different interface scheme may be suitable. You know, it's not a general suggestion.
Yeah.
I suggest these ones only for IB-LBM. I think you used the immersive boundary method, but you did not use lattice Boltzmann method for your simulations.
Yeah. So that's what actually I was thinking that, for example, we have seen a lot of those applications in low Reynolds number flows, and people usually struggle with IBM when they go for high-speed flows. So I wanted to understand that how effective the technique could be, especially the combined IB-LBM for like high-speed flows, where we can go into compressible regimes and perform some LES simulations. So, okay, thank you. And my another question was about, I think on slide 14, you were talking about distribution functions to identify the interfaces. So my question is that, do you need to use different distribution functions for different applications or for different shapes of the bodies?
I believe that we should have, like a mesh graded study that we used for a different problem, we can test them for different problems too. But I found, as you can see here too, for different scheme, we have no much differences between different diffuse interface results. We only have we have the most differences between the sharp and diffuse one, but all diffuse interfaces has a very similar results to each other. I can say that in general, nobody do this work. Most of them use an interface scheme and use it for all their applications. In IB-LBM, as I told you, most of them use the diffuse one. But as I told you, no, I think that you can find your perfect interface scheme. You may develop your code based on that, and after that you can use it for all of your applications. Regarding to my experience.
Yeah. Thank you for your great answers. So do we have any question from other participants?
Can I
Yes.
ask you a question?
Please, Dr.
Yeah, thank you very much, Amin, for the great presentation. It's very, very informative and impressive. I have a question about large displacement. When we have a flexible body in the domain, when we have a large displacement using LSM and LBM, um, how we should treat the algorithm not to, miss the data, because when it passes a couple of lattices rather than one lattice, how should it be treated? Because in lattice Boltzmann, because I believe needs to be explained first. In lattice Boltzmann, each iteration means some delta t, and we need to convert it to physical delta t. But when we solve it with lattice Boltzmann, we are in the lattice Boltzmann environment. How should we treat that? This is one of my students' issue that when she wanted to solve that by very large deformation, sometimes we get instability.
Yeah. I should say that the investigation on this matter are under developing. This problem are related to the lattice spring modeling of your works. And I know that the time scale are different between these two ones, and it leads to many of instability problems. To be honest, or simulation are the same. We can capture the flexibility in somewhat, but I think that if we want to solve this problem, we should work on the elastic modeling of our problem. Maybe we can say that we can use other models, not the spring models. But to be honest, I didn't work on a large
Deformation.
deformations.
Yeah, that's a very, very interesting area, especially when we solve problem in lattice Boltzmann environment and know how we can expand it to getting the Navier-Stokes equation. That's quite interesting. I think, if you agree with me, I think we need to combine these equations first in a lattice Boltzmann environment and then try to expand it using Chapman-Enskog expansion or another way to find the similarity between the developed equation and the Navier-Stokes equation, including force.
Yeah, it's a really interesting jobs, and also I think it's need a very vast knowledge on the lattice Boltzmann and also the Chapman-Enskog expansion to recover the Navier-Stokes equations related to this problem. I think it can be a new research.
Let's discuss this. This just came to my mind, and I believe we should think about it. This can be very, very interesting. Thank you very much, Amin.
Thank you, Dr. So we have other questions from the participants.
Dr. Khaled, hi.
Yes, please ask me.
Hi.
Hey, can I ask a question?
Please go ahead.
Yeah. Dr. Amir, thank you so much for your great presentation. It was really informative. Just one question came to my mind. So when we are choosing the number of the points that we are using for interpolating, does increasing the numbers affect the stability or our results? You showed the numbers up to 4. So does increasing the number affects our calculation?
Yeah, thank you for your question. I have a discussion with Dr. Tarok on this problem. Indeed, we speak about the number of the lattice or lattice Boltzmann mesh. But for Lagrangian nodes, again, I do some researchers I do some mesh grade study for Lagrangian nodes independent to the lattice Boltzmann domain. And we increased the number of the Lagrangian node to find out what happened to my simulation and the accuracy of that. For your question, I should say you should do a mesh gradient study for that. You should increase the number of the Lagrangian nodes, and you can find that after a certain number of the Lagrangian points, you have no change in your results and also in the accuracy of your results. And this number of the Lagrangian nodes is a suitable number for your simulation. Again, it's depend on your problem. You may have a filament, you may have a circular particle or other problems. But you should be aware of the minimum number of them. You know, we have no limited on the maximum number, but we have some limitation on the minimum number of them, especially for the filaments.
I get you. Thank you. And another question. So when we are combining LSM and LBM, so delta X in LSM is different than the LBM one, right? So in some studies, I have seen that they insisted on having bigger delta X in LSM rather than LBM. So for example, if delta X in LBM is 1, delta X in LSM should be more than 1, 1.2. But in one of your studies, one of your publications, it was mentioned that it was a great study on the delta X of LSM, but it has been mentioned that having a smaller delta X in LSM gives higher accuracy.
Yeah.
So I was a little bit confusing. I'm not sure if we should choose the delta X of LSM more than LBM or lower than LBM.
Yeah. You know, in our simulation, we use delta X lower than LBM delta X for all our simulations. And again, regarding to our experience and also our resulted and comparing them to the benchmark problem, we found that the lower number of delta X leads to more accurate results. But as you mentioned, there is no limitation on delta X for LSM modeling in comparison with Lattice Boltzmann delta X. You may have acceptable results by using the larger values for delta X. But you should be aware of the accuracy of your models. You know, but these two ones are completely independent to each other. So I think that it's not true to compare your delta X in LSM with delta X in LBM. You should work with it independent.
Okay, so you mean that if they're mentioning that it should be more than delta X and LBM, but it is not completely true. So they should be treated independently.
Yes.
Okay, thank you so much. Thank you.
Yes. So thank you so much, everyone, for participating in the event. And hopefully we would have the next seminar, because we would be having one speaker every 2 months. So this is how we are planning for it initially, and we have recorded the presentation, and we would put it on YouTube as well for your future reference. And please share the invitation with your colleagues, with your research network, so that we can widen the impact of this seminar series, and we can have more people on board. So thank you so much once again, and have a great weekend ahead, and be safe, because there is a lot of snow outside. So
yeah.
Dr. Liu.
I just want to say thank you very much. This is not my area, okay, but very interesting, very informative. Okay, thank you.
Thank you so much.
Thank you so much.
Thank you.
Okay, thank you, everyone, and have a great rest of the day and the weekend.
Thank you
for
so
the
much, Dr.
interview.
Khaled.
So much.
Everyone, have a good day.
Okay.